So, hello everybody, and welcome back to another Thursdays at BrIAS seminar event. Also, today we will have two seminars like all other Thursday. So, in case you have doubts on when we are going to have seminars, it's on Thursdays. And so, today we will go more on, we will have a first talk more about networks and how to virtualize them. And we will have a second talk more on the robotic side. But I want to introduce our first speaker, that is one of our senior fellows here at BrIAS, is Giang Nguyen from the University of Dresden. And I am pretty sure that yesterday we spent a long time speaking together about his research subject, which I find very interesting because it touches how the network influences reality and influences the need for specific performance for control. So I am leaving him the stage. So please, Giang, the stage is yours.
So good afternoon, everyone. So first of all, thank you very much, Emmanuel, for the very kind introduction. I'm Giang Nguyen, and if you, from my last name, if somehow you guess that I'm from Vietnam, you are 100% correct. And I have been living in Germany over the last almost 15 years, from doing PhD, postdoc, being a founder of a startup, and currently I'm assistant professor at the Technical University of Dresden. And today I would like to contribute the talk about softwarized networks. So not okay. So particularly the software aspect of communication networks. And so the goal is that we exchange the ideas, and hopefully we can find like interesting synergies, how the software networks can contribute and also can learn from robotics, AI, and automations. So first of all, let's have a look at the current status of the network, the largest network in the world, which is the internet. So with the internet, currently we have any problems sharing information, ideas, video, audio across the globe at any time. So it is democratizing the access of the information. However, from our viewpoint, the internet would need to evolve into the next generation, which is a tactile internet that can democratize the access not only to the information, but also to the skills and the expertise, where the human can learn from the robots, and the robot can also learn skills from humans. And in order to do so, we would need the sense of touch. And when we look at the current status of the internet, it cannot fulfill the requirements of conveying the sense of touch from one point to another, mainly due to the large latency. And therefore, our approach is to softwareize the networks in such a way that it should be programmable and subsequently will be flexible. But at the same time, the flexibility will also allow for to speed up the network and also to make it more resilient to eruptions. All right. So how we see the networks and how we see the interaction between the human and the machine. So first of all, I think until now, probably we have a common belief that at some point we will have completely autonomous systems with the help of automation, AI, robots, so that the human might be at some point, we just need to sit down and then let the robot do the job. But until then, um, uh, there might be some transition. So the robot and the human will need to collaborate and to learn from each other. And even with completely autonomous systems, robots and humans still interact. And currently, the interaction will need a communication network in the middle. Yeah, so what is the challenge in this scenario? So first of all, the challenge coming from the human side. So we humans, we are very sensitive and will be affected by the latency. So in this case, the human with the virtual reality glass will try to catch the ball in the real time, right? However, by the time that the human realized that he or she can catch the ball, it was already too late, right? Simply because of the whole conversion of the signal from the real world to the virtual world and so on. And needless to say about the sensitivity of the human brain, different genders, or different in the expertise, or maybe different in the ages. And at the same time, machines are also are affected by the delay. So until now, I think with the control community, we are pretty understood that we are pretty certain that the networks with the loss, latency, and particularly the jitter are not reliable enough to decoupling the control far away from the system, in this case, the robot. And if we have the large delay with the closed loop control, then the system at some point will become unstable or maybe even dangerous when interacting with the human because it cannot control the behavior anymore. And why it is the case? We thought that, okay, the network just deliver the service. So nowadays, if we have the service we would like to use mainly with the cloud service provider, then there are some connection with switches and routers. There shouldn't be any problem. The reality is, in the middle, there are a bunch of network functions that we are not very visible to the end users. They are firewalls, WAN accelerators, cache, and also like for security, we would need intrusion detection and so on. So all those network devices, they are specialized box in hardware to try to optimize for the performance. And there are not a few of them. And actually, there are many of those in a typical network. And all of those, they contribute to the complexity of the network and also eventually to the flexibility and the latency of the network. So what a softwarized network would look like. So if we would go from the current state of the network with dedicated hardware, then each of the network functions, for example, firewall, intrusion detection system, IDS, or maybe one optimizer, each of them running on a dedicated hardware with operating system and then with the algorithm on top. Even within, if those network functions or devices coming from the same vendors, there are already complications when configuring them manually and connecting them physically. And imagine if each of those network functions coming from a different vendors, right? Slightly different interfaces, slightly different commands, and so on. So the management of those networks will become very complicated. And therefore, with a softwarized network, there will be a transformation from dedicated hardware using now commodity hardware. Typical switches or routers that we can buy over the market, typical servers, so that we can run virtual machines, or maybe Docker container. And on top of that, we can implement those network functions like firewall, intrusion detection, or maybe one optimizer completely in software. And then what is the benefit? Those functions will become like going to a supermarket. Depending on our need, we will select some of those and then connect them in software completely. In this case, we would need only 2 network functions, but we can also select 3, 4, 5 network functions on our need. And what is the benefit of this? So the first benefit is the reduce of latency. How can that be possible? So let's have a look at the current state of the art when we deploy a service between the human and the robot. For the service nowadays, typically we would need cloud service provider like Amazon or maybe Microsoft Azure and so on. And then we deploy the service there, having a connection from both sides, human and robot, to the cloud. And then somehow they should communicate and interact. With this case, the data have to travel from the human to the cloud, maybe 100 kilometers away, and then back to the robot. So the round trip time could be 50 or maybe 100 of milliseconds, simply because the information has to travel for a long distance. And since we have a physical distance between the two entities, and we are limited by the speed of light, so there are some fundamental limits that we cannot exceed in this case. However, with the Softwarized networks and the flexibilities, we can potentially change the transmission of information between the two endpoints. And in this case, the human and the robot can be connected using a completely shorter distance. And the service will be deployed at a very close distance to either the robot or the human or both. And we call this paradigm mobile edge computing. So we leverage the computing capabilities inside the network to implement network functions. Another advantage of this paradigm, once we have the infrastructure of the mobile edge computing, then in principle, we are able, and we should be able, to implement and deploy new network functions, or maybe new applications in the network, so that we can leverage the low latency, since now they will be in software. Okay, so I hope that until now I motivated us sufficiently so that I can move to the 3 highlights of my work that I would like to share with you today. So in the first line, the first contribution is to tackle the computing latency in Softwarized network. The second is about audio processing, so mainly how we can leverage the Softwarized infrastructure of the network to do something else, so new applications. And the last highlight will be about the resilience, since we have the software, not the dedicated hardware anymore, and the software will share the same infrastructure that they might need to compete with the resources with one another. So resilience could be a concern. Okay, so now I will jump right into the first work, trying to reduce the computing latency. But first of all, let's have a look at the scenario that we have. So the block on the left-hand side is the building blocks coming from the sensors to the mobile communication system, and then going back to the mobile communication system, and then to the actuator. The block on the right-hand side is the mobile edge computing server. Okay. So research have been shown that in order to have the real-time, perceived real-time interaction between the human and the robot, in this case teleoperation for example, then we would need to fulfill 1 milliseconds round-trip time. For audio and video, normally we can tolerate higher latency. For audio, for example, up to 5-10 milliseconds. Otherwise, might hear the echo and so on. For video, we can tolerate even larger latency, up to 30 milliseconds. But now, with the sense of touch, we have only the delay budget of 1 milliseconds. And if we have to deduct the delay from other components, like sensor, actuator, and so on, then we have only roughly a third of a millisecond for the computing. And we already did a measurement study, and it turns out that by no surprise, we cannot meet that delay. Okay, so now we would like to pinpoint, so what is the bottleneck, and how can we do with it? When we look at this from between the two PC or maybe two servers with exchanging the information between the two virtual machines, then the information will have, or the data will need to travel over many components. And many of those, for example, with the bridge, the physical network, and so on, we consider them as state-of-the-art, and we will take them as they are because we have less influence on how the device will be manufactured. We have less influence on the vendors or maybe the operators. However, what we can have the influence is how we implement our network function inside the virtual machine. This is, maybe we can have a novel approach for doing this that can help us to reduce the latency. We will go one step deeper and see what is inside the virtual machine that can potentially hinder us from achieving the goal. And then we found out two observations. But first of all, inside the virtual machine, or if we build like an application currently, and particularly the application that need to exchange information with the outside world, we would need CPU, of course, as always, but also inside the operating system, we would need the kernel space and also the user space, where the new network function will be implemented inside the user space, and the networking functionalities mainly reside in the kernel space because they need to be optimized. They also need to be pretty small. Okay, and then there is two bottlenecks. The first one is the CPU. Every time there is a new packet come into the system, there will be interrupt. And then the CPU, whatever it is doing now, it has to push into the cache, take the new data, trying to do it very quickly, complete, and then resume with the work that it has done before. And if there are so many packets coming in, and the CPU cannot keep up with the rate, and then we have interrupt all the time. And eventually, the context switching between computing and storing, caching, and so on, it will decrease the overall performance of the system. The second bottleneck is the read-write operation of the data when there are data passing between the user space and the kernel space. And the reason is that all the network functions, they have to pass through the network functionalities in the kernel space. So always exchange of data. And every time there is a copy read-write operation, there are overhead. And our approach is that, okay, we need to remove those bottlenecks. we would like to eliminate completely the context switching. And then we have a look into the set of network functions that we implement and then we deploy, and see which one should be feasible to be implemented in the kernel space and then stay there for the whole time, and which network function should be or must be implemented in the user space. For example, due to the availability of the library. Nowadays, if we program, we have to use library. We cannot program from scratch. Okay, so these are the category, but of course we would need some trade-off, or maybe some, for example, we would need to trade the storage, in this case, the resource that we provide for each network function, not sharing one virtual machine anymore, but each one will have its own virtual machine. Okay, and we call our strategy like Canvin. Now, if we look at the strategy, after we change it, so we have completely different virtual machine, A, B, and C. They are in the data plane, okay? And some network function, in this case, basic network function 1, will stay completely inside kernel space. Okay. And then once the data was processed inside this network function, it will go out and never go back to the kernel space again. And then the data will be subsequently be processed inside another function 2 or 3. And they are more advanced, so more complex, and they would need to be implemented inside the user space. What do we achieve with this strategy? Let's have a look at this plot. So on the x-axis, we have the round trip time. On the y-axis, we have more or less the distribution. Now, we notice the black line is the threshold, a third of a millisecond we would like to achieve, while the other line at the very right-hand side, they are the state-of-the-art, which is the centralized approach, sharing virtual machine and then sharing the CPU, context switching, and so on. And I think it is pretty obvious from the graph that the state-of-the-art rarely or barely meet the requirement of the latency. On the other hand, our approach, Canvin, depending on the packet size, we can move the line way behind the threshold, so meaning that it can meet the threshold most of the time. But how far can we move the line to the left-hand side? So there is a physical bound limitation, which is the lower bound of the latency that we can achieve when we do nothing. Data coming in, going out immediately. And in this case, so our conclusion in this case is that whatever the technology provided us, there will be like 10 times increase of the latency in the state-of-the-art. However, we can reduce the latency significantly close to the lower bound. And if the technology advances regarding the hardware, operating system, and so on, we can always move and follow the lower bound. All right, but there must be a trade-off. And in this case, we see that we have very little room for more advancement. Right? And the second disadvantage is that we have to sacrifice in the bandwidth. We cannot process very quickly. And therefore, in the subsequent study, what we would like to learn is to see how we can apply this current framework to process the data, maybe for a different kind of application that doesn't really need extremely low latency, but have a requirement for more bandwidth. And in this case, we selected audio. I mean, we could jump directly to video, but maybe step by step. So this is how our approach. From haptic, we go to audio. So, and the application in this case is audio processing. So in factories, surprisingly, audio is a very common practice to monitor how the machine works. One of the reasons is that with the video, we always have to handle the obstacles. Right? With the audio, we don't have such a problem. We can deploy microphones in many places. And from the experience of in the factories, we learn from the people working in the factory that normally a malfunctioning machine will cause a very strange noise that happen way before something really happening that the camera can observe. Okay, but then the challenge here is that microphones, they collect everything. All the audios they collect, and therefore the audio from one machine will interfere or maybe will be combined with the audio from other machines. Luckily enough, this problem has already been addressed by a setup or family of algorithms, which is a blind source separations. So by using such algorithm, one can restore a rough estimation of the original audio sources. Here, so we have some formulas, but basically what we collect at the end is a set of mixed data, and we need to apply blind source separation algorithms to separate them. In a common approach, we would like to send the data, so collect the data, send them over the internet to a cloud provider, and then because the computing resources over there is abundant, and therefore it would help us to separate the data and have the result very quickly. However, if we do so, we need to pay two things. A large amount of data coming to the cloud provider, we have to pay one time. And if the computation is complex, the calculation will take a long time, we need to pay also for the computing. And it is not very cheap. This is how the cloud provider, they make the earning. And therefore, what if we can do two things? We distribute the computation over the network devices in the middle, along the path, so that the data will be pre-processed somehow. And hopefully that at the end, the pre-processing will significantly reduce the computing load at the cloud provider. And also, we also hope that the data that we send over the path can be reduced, so that eventually when the data coming out of the local site to the cloud, it was reduced. So we don't need to pay too much for the data transfer and don't need to pay too much for the computing. But then we have two challenges. The first one is the current blind source separation algorithm is centralized. But now if we want to distribute the computing load to a sequence of network nodes, we need to transform such algorithm from centralized to decentralized. And the second challenge is the current networking is designed for send and then transfer. So it doesn't want to store the information. So as soon as the network device would receive the data, it will try to send out as quickly as possible because this is the job that it should do. Now we try to tweak it a little bit so that not only it is receiving and sending the data, but also try to compute a little bit, but without causing too much delay. So first thing first, we look at how we can transform the algorithm. And then we look at the algorithm can basically be divided into 3 building blocks. So data extraction, data estimation, so doing like in several rounds until it can really estimate the original data, and then finally to collect and recover the data. Okay, now and therefore we will do the separation and data extraction and data estimation repeatedly on the network devices along the path. And at the end, because the data recovery will only be done once, we will keep it at the end server. Then, of course, we have different strategy. Either we try to compute as much as possible at the early network nodes, or maybe we try to somehow balance the load between the network nodes. Okay, 2 strategies. Now coming to the second challenge about networking. So, as I said before, if we rely on the current network, data coming in, compute, data coming out, then we have like a stop and go, which is very slow. If we transfer the data for the computing, and then we look into the data, then probably we already violate the one of the principle of networking, which is end-to-end. So we should not change the data at the intermediate nodes. And therefore, our approach is we need to introduce one additional module doing the 2 things. One is that it should have the memory to look at the data and then to decide whether this kind of data should be forward right away or maybe should be processed. All right. So quickly about the result. So the yellow line is state of the art, or maybe this is how we would like to compare against. And every subsequent line will represent the number of network nodes that we introduce between the sender and the receiver. So could be 1, 3, 4, 5, 7, and so on. And then we observe that the more network nodes in the middle that we have, we can reduce the delay, the overall delay of the data processing, so up to a third. And the interesting thing is that if even we introduce or we pre-process the data with 1 or 2 nodes, the gain is already pretty significant. And also confirming to our observation, so the residual computing load at a subsequent node will be reduced. All right. So now we also learned that with the Softwarized network for certain applications that doesn't need very super low latency, but with the requirement for high bandwidth, and depending on our design, we gain something. The third contribution that maybe I will go pretty quickly over is about the resilience. So how the software implementation of the network function or new applications can or should be designed, and the network, how it should support this kind of application design to improve the resilience. So it means that if the function failed, then the backup should be up and running as quickly as possible. Or the best thing is there's no disruption, no interruption between the two events, failing and resuming. And currently with the cloud computing, there are practices which is already there in cloud computing. So doing the migration of the whole virtual machine, or maybe more lightweight, is to migrate only the application part, right, using, for example, Docker container. We ask ourselves, can we do even better? So not the interruption time, not only in the order of seconds or tens of milliseconds, but already maybe a few milliseconds. And therefore, we came up with a scheme which is a state design. By state, we define it as intermediate results of a computing of a certain function. And for that, we divide the state into two parts. The part that doesn't change very often or optimally doesn't change at all. For example, if we consider IP address, port number, and so on, they rarely change for one client. But the other type of state is the temporary, the temporary result of the computing that change very often. When we look at the design in the state of the art, there are basically two approaches. The one is using like very reactive, right? So when we decide that we would need to replicate a certain application, then we transfer the state. The new application is up and running, and then we remove the old one. This is a very reactive. However, in reality, there are events that we cannot be react. If we react, it might be too late. For example, failure. If an existing application fails, it will not respond. It will not be there and to transfer the state. And therefore, another approach is to be very proactive, sending the data, updating all the time, with the drawback that both instances of the application have to be up and running, or maybe we have to store the state into external database, which reduce the performance. And then we came up with our own approach, and we call it StateOS, because it is basically provide application on top, so it provides an abstraction layer for application to build their application that can support the scalability, fault tolerance, and also acceleration. And it supports both strategies, reactive and proactive. All right. So we measure whether this StateOS can really help in increasing the resilience of the system by looking at the time needed to copy the state from and then transfer it from one place to another. And for depending on the number of flows, which represent the workload in the system, the saving can be up to 60-70%. All right, so to sum up with the highlights that I have already presented, first of all, we tackle the challenge of reducing computing latency inside Softwarized networks. We came up with a solution, Canvin. Second, we would like to see whether the Softwarized infrastructures or the networks can be used or leveraged to do something else, maybe with higher latency but larger bandwidth. And in this case, we came up with fast ICA, which is the independent component analysis for audio processing. And the last contribution that I presented today was about StateOS, which tried to address or improve the resilience of virtualized networks. And the approach that we did was pretty pragmatic, as you observe. We try to find out what is going on and then try to make it better. And the overall theme of research group, the research of my group is try to collaborate. And in order to collaborate, we are willing to go extra miles, not only to focus and stay within our circles of networking, but also try to learn new application, new domain. Like in this case, we try to learn audio processing, or maybe we try to learn into the kernel space and so on. All right, and the work that I have presented it's not that I could do alone, but it is a whole group of the team that have been working with me over the past 3, 4, 5 years. Now, looking forward, how the Softwarized network would contribute to robotics, AI automations. So first of all, I would like to sketch a few ideas. So first of all, after the discussion with Emmanuel, maybe the network can also will be a reliable channel to provide the reference for traditional control systems. Right? However, what I'm also interested in is to apply or to adopt some of the control theory into the networking part, because in the networking, we need to control something. For example, the flow controls, or maybe the congestion control. And maybe some control framework, like explicit reference governors, with the advantages of low computation costs compared to like optimization of the constraint control, that might be beneficial for the networking part, where we need to deliver things pretty quickly. And at the same time, so in parallel to the academic perspective, I also would like to contribute into the domain of robotics, which could also have the impact in the society in a very direct way. In this case, I'm in the collaboration with BRAM, and the application that we would like that we find the synergy is the set of robots that collaborate with one another. They are specialized robots. Each of those will be very good in certain things. Some will be static or stationary, others will be mobile. And they collaborate to achieve a common goal. And since they need to collaborate, they need to share information. And in this case, the sensors from the robots will be collected over the network to a centralized server for the aggregation to understand the environment, and from there, one direct application is to guarantee safety, avoid collision, and so on. And currently, we came up with a framework which is flexible, based on software that components inside each entities can be deployed using Docker container, and then depending on whether the delay budget, the CPU budget, we can decide whether we would like to prioritize for compression. If currently the data will be huge, then we need to compress before we send out. Or if we can relax on such constraint, then maybe we send the data right away. All right, so I hope that this is simply the starting point of the discussion, and I'm also open to other discussion and your ideas. And first of all, I think regarding robotics, maybe in a few minutes, Bram will tell you way better than I did. So, but anyway, questions are welcome.
So, are there questions from the public?
Please. Okay, Bob.
Thank you. Thank you. How you would you also, so the one thing is also the hardware, and how your research can influence the developments of the hardware for better communication. Because now you said you use components available, but I don't think robotics is yet so powerful. But imagine in the future that we really can dedicate, make the communication devices that focus on the needs of robots.
Okay. So regarding, I think it makes a lot of sense. So we try to, so one of the goals, so maybe I need to take a few steps back to answer the questions. So one of the goals of transforming the network functions or the network architecture from dedicated hardware to software is that we can simplify it. And once we can simplify it, we can really narrow it to a particular application. Depending on what are the functionality that we need, we will tailor it. Now coming to the hardware, so currently our approach is to take whatever available in the market. However, I hope that by simplifying the software to certain level, we realize that this is a set of functionality which is simple enough that can be implemented in the hardware. Nowadays, there are also hardware that allows for programming and reprogramming, and maybe that will be like the platform for implementing the innovation inside the network that will be optimized for a particular application.
Yeah, because I think now communication devices are mainly for mobile phones and computers with those requirements, but not including what we need from robotics. So we need to adapt to what is available. And of course, I think we need to the opposite. And another aspect is, one thing is about communication, but what about also indoor localization and positioning? Because there are a lot of signals between the different agents. I will explain a bit more, but we use ultra-wideband localization. But it can also be a 5G network and so on, but also there we see that the devices are not made sometimes to make that possible. And also maybe there we can combine communication with also relative pose estimation and indoor GPS system.
Yeah. So before addressing the second questions, I would like to comment on the last part that you said. It is also the purpose of joining as a fellow of BrIAS is also to work with other teams, for example, robotics, to learn what is the current limitation of the network to support a certain domain, and we would like to learn from it, to see what are the aspects that the network can do better. Because from our own experience, when we approach those things, those challenges, like in audio, then by digging deep into such a domain, learn from those, we found some solution, maybe not the best one, but one step better than the previous solution. And regarding the second question about sensing, I think it is a super interesting domain. And in particularly in the next generation of mobile communication system like 6G, there is initiative to combine communication and sensing together, so that we don't really need two systems, but simply using using the mobile network, the signal, and then to use it for the sensing at the same time. But also to combine the mobile communication networks with other technologies like ultra-wideband and so on. Because for ultra-wideband, compared to the cameras, it has a huge advantage in privacy, for example, privacy protection. So I think it is. Unfortunately, I don't have any answer for such a huge problem, but I think there are some direction that we can explore. Thank you.
Other questions? Oh, a little bit shy today, but well, I might have a few. As you know, I worked in a similar problem from the other side, so from the side of control at the beginning of my career. And I remember already 20 years ago in a plenary talk by Andrea Goldsmith in one of our major conference that she was presenting us the need to think about co-design between control and communication. So this is something that I've heard in multiple conferences, and then somehow it always remained, at least in our community, a niche. What happened in yours? Now I'm curious.
I think it is the right time. I think even though the topic was research 5 years, maybe 10 years ago, but I think this is the right time because we also receive the demand from actually industry. They are also interested in control and communication co-design. I'm not quite sure what is the motivation behind the industry, I don't know, but we receive the question from industry that they are also interested in this topic. So if there is a chance that maybe we can explore more about this, then of course I'm very keen on.
Another question that is kind of associated, that is, it's always, we often see trying to do control, try to do robotics, using existing network, using existing protocols. The real question is, aren't the need of, so the need of the current internet is to transmit data, to transmit videos, to transmit this kind of stuff. It's not about real time, it's about bandwidth, it's not about latency. So a question is if it's the right path to follow, or if we should think for this future application more of a different topology, more of a different way in which the network manages the packets, with much more close to the physical layer rather than too many abstraction layers. I don't know how you see it.
Yeah. Okay. So I have to admit that so this is often the case that when we have there is a collaboration between the control and the communication communities. Eventually, the control community have to assume that the network is unreliable. I think this is true, but also sad. And currently, the networking community, we are trying to improve it, right, to increase the reliability of the network, reduce the latency, trying to have not only the long tail of the latency, but maybe more skill to a certain degree. This is a work in progress. However, there are some initiative, particularly it is time-sensitive networking, which is like the idea in local area network and in the industry. And now would like to more or less employ the same idea with the synchronization of the clock between the stations and the receiver, sender receiver and so on, so that they can really schedule when to send a packet, when to receive the packet. Normally, for networks like Wi-Fi, that we don't have any dedicated frequency. It is shared frequency. Anyone can access, can sense Wi-Fi. I think it might be challenging. However, for dedicated bandwidth, like in mobile communication system, then nowadays with campus networks, for example, that one can have the full control from the core network to the RAN, and then with the frequency, dedicated frequency, I think we have some hope that we can really have the control over the behavior of the devices inside the network. Oh, sorry.
I don't know if this makes any sense, but for this very specific types of communication, like you're controlling a physical device, is there any way to have predictive communication? So in the video that he showed, it seemed that there was trembling because the moment that the thing was going down, they were going up, but you can predict that the movement is going to go a little bit in that direction, particularly if the device in the sender has a camera or something that is very specific to the application. I don't know if that can be done or has already been done.
Yeah, so I think it makes complete sense. So as a matter of fact, also we did in SETI the work with anticipation. So the motion of the hand when we try to grab something, so normally we can detect this even up to almost 1 second before we grab the object. So we can anticipate it. And it is also our long-term goal that we use the gain in the latency to inform the network and then to better schedule or maybe better optimize network resources to avoid collision and so on. So I think it makes total sense. Thank you.
Well, I will close. Oh, there is a question, so I will not close.
I have a question about the robots that are being used in surgeries. They use 5G networks. How dangerous it can be with this problem of latency?
So the latency, the challenge of latency in remote surgeries. Yeah. So we, it is a real challenge we'll address in SETI. So SETI is a whole research cluster consisting of almost more than 30 professors and more than 70 PhD students, postdoc, and so on. And this is one of the scenarios that SETI tried to address. So in phase 1, we address this as a training for surgery. So we try to, because really to guarantee low latency, reliability for the wireless network, for such application with stringent demand, strict demand like surgery, it is really a challenge. But in SETI, what we try is to meet the demand for training a surgical person. And in the next phase, we will try to address this. But this is ongoing work, and this is really a challenge.
Okay, so I will conclude just with a small observation question, more or less. That is, when I was making you the question about co-design, of course, answered for the side of telecommunication. I must say that as a control guy, although we have spoken about this co-design for a long time, still it is very rare that in a real implementation we implement the state of the network as one of our control variable, while instead it's very important because if I know that the network is poor, I know that I don't have to do aggressive maneuvering and vice versa. So there is a link there. And somehow also I'm looking at Bram because together we are some of the men responsible of the course of robotics. This is aspect that, for instance, we never expose our students to. Instead, it's something that it's absolutely relevant. I don't know how you see it.
It's really a challenge, and I'm excited to to address this jointly.
Okay. So with this. I go in the camera field. So with this, I want to thank once more Giang for the very interesting presentation. And as usual, I invite you for our coffee break, and then we will have a second very interesting talk by Bram. So see you in 10-ish minutes.